So, definition of specific heat capacity. It's kind of wordy, but it needs to be. It says the amount of heat required to raise the temperature of 1 gram of a substance 1 degree Celsius. Now, it needs to be per 1 gram, and it needs to be per 1 degree Celsius, because if you didn't have it per gram, how would you be able to compare the two individual things? Like, if I had 100 grams of something and 10 grams of something else, would we be able to say that the amount of energy needed to raise the temperature of each of them are going to be relatable? No. Okay? But if I'm saying how much energy would it require to raise 1 gram, 1 degree C of your pot, and 1 gram, 1 degree C of your water inside of your stop. Okay? You'd be able to compare and make some distinctions here. What we're going to see is that what we see in reality is that things don't all heat up at the same rate. Some things heat up faster than others, and some things heat up slower. Would you all agree with that? Everybody?
Yes.
Okay? So here are the units. The amount of energy in joules required to raise 1 gram and 1 degree C. Okay, so let's compare. Let's say I have like 0.52 joules need to raise a gram 1 degree Celsius. And I have 4.18 joules needed to raise a gram 1 degree Celsius. Which of these two numbers, let's say this is water, and this is aluminum. Which one's going to heat up quicker? Why? Because it takes less energy to heat 1 gram of it 1 degree Celsius. Water takes a lot more energy to raise that same amount of mass, the same temperature. Are you seeing it? So, when I say something has a low heat capacity, specific heat capacity, what conclusions can you make? It heats up fast, more quickly. Okay? When you have something with a high specific heat capacity, it heats up a lot slower. Believe it or not, water has one of the highest specific heat capacities of all things. Water is unique in a lot of ways. What do you think is the main reason why water has a really high specific heat capacity? God, it's itchy.
Because your body's hot.
Because your body's hot.
I don't know.
That's a good guess. What is beating down on us every single day?
Oh, vapor pressure and the atmospheric pressure.
The sun. Or the sun.
Oh.
Okay? And the sun beats down on the earth a ton. And if the earth wasn't mostly made up of water, what would the temperature of the earth be?
Skyrocket.
Very hot. Really hot. So the water can absorb a whole bunch of that sun energy without seeing a drastic what? Change in temperature.
So why can you boil water in like 2 minutes?
Well, you can boil water in 2 minutes because
Using something hotter than the sun's rays.
That stove is hotter than the sun.
no, it's more precise radiant energy.
The distance from the sun to the earth is making it cooler than what it is.
Yeah.
What it is, it says it's more constant.
It's a lot more concentrated.
Wait, wouldn't you think something that's like more viscous would be heat up like at a higher specific heat? I don't know. Because it makes it stay together. Yeah, like it's also like honey. Would honey heat up faster than water?
I don't know much about the properties of honey.
Okay.
But I do know that water is like one of the highest specific heat capacities, so it takes a lot longer. Yeah, there's probably water in honey. Water's in most things. But, yeah. Okay, so then that bottom part says lower specific heats are going to show up on warming curves as steeper lines. Okay, so this would be an example of something with low specific heats. This is what it would look like with high specific heats. Do you notice how it took longer to get a temperature change. Because it requires more energy to change the temperature. Okay, here, it didn't take as long to get a temperature change because it had a low specific heat, and so therefore it heated up faster, and we saw a change in temperature happen faster. Does that make sense? Why low specific heat is going to show up as steep lines on a heating curve, and high specific heats are going to show up as more gradual slopes. Everybody understand that relationship conceptually to the graph? So here's some examples of some common things you may have seen before and their relationship to each other from a specific heat capacity. Mercury allows heat to transfer and heats up really quickly. Only requires 0.14 joules to raise 1 gram at 1 degree C. Okay, you can kind of see most of the metals are here. We start getting into some of the non-metals that don't conduct heat very well and don't heat up very fast. And then look where water is.
Oh wow.
Okay. All right. There's an acid. There's a well-known hydrocarbon. Also an alcohol, which we know alcohols are really volatile. Okay.
How can oxygen be like so different from water?
Wait, is aluminum contact too?
I don't remember.
It's no, it's on the next one. But
Oh, I just made that up. I knew what water was. I had no idea what aluminum was.
oh, got it.
Yeah, I was just using that to like show you.
Yeah.
Sorry, I maybe should just wait to the slide. But I did not know aluminum's specific heat capacity off the top of my head. I probably know it more now that you say that. Okay, so here is our specific heat capacity equation.
What, man?
This is also known as our
Cubic. But
calorimetry equation. Calorimetry.
okay.
Remember we talked about the calorimeter yesterday? Okay. Now, you're probably familiar with mass, although notice what the mass's unit is in. It's actually not in his SI unit, because his SI unit is kilograms, but the reason why this is in grams is because the specific heat capacity is in what? It's got grams in it. Okay, so that's why your mass here is going to be in grams. Okay, so what will end up happening is your grams will cancel out with that gram. Your temperature will be in Celsius, will cancel out with that degree Celsius, leaving you with the unit for joules, which is what Q is, or is our thermal energy. Now, if you remember, we said that a calorimeter is used to study heat transfer. Yes? And I gave you an example where you had a calorimeter, okay, and you plopped a rock in it. Okay, if the rock was really hot, what happened when you put the rock in the water? The water heated up and eventually they reached what?
Equilibrium.
So let's say if I knew the mass of water, let's just say the mass of water was 20 degrees or 20 grams. We know the specific heat of water, how fast or how much energy it takes to heat it up. Okay. Is that right?
Yeah.
I'm drawing a blank. Okay?
Are we gonna have to memorize
No.
that?
Okay, let's say in this situation we put an object in that caused the change in temperature or caused water to increase 20 degrees. Okay? Someone just quickly plug this into your calculator for me. Somebody.
I just got it.
Oh, maybe.
So 400 times 4. 1200 something?
16.
Or not?
1672.
Okay, now I want to make note of this. Okay? First off, the temperature went up for water. Does that mean it probably absorbed the energy or released it? The temperature of water went up. Does that mean it absorbed the energy or released it? It absorbed it. So it gained this much energy. Couldn't you then make a logical, rationalized thought process here? Wouldn't we be able to say then that the rock gave off that much energy?
Yeah. Unless there's another.
So do you see how we used water to figure out the energy given off by the object we put into it? And so what they do is they do this with chemical reactions. A reaction will happen in a calorimeter. They'll study what happens to the water and deduce, oh, well, if the water gained this much energy, it had to come from where? The reaction. And vice versa. Pretty cool. So.
Sorry. Well, I didn't know.
That was really snotty.
Sorry.
Okay? Problem number 1. Okay? Okay, joules. Which symbol of our calorimeter equation had joules in it?
Q.
Q? Okay, of thermal energy is added to a mass of? Okay. It says added to 50 grams of water at a certain temperature. Okay, first off, we don't know what change in T is. Do you guys remember what change means? Okay, yes. So could I say the
Final
change?
minus.
Yes, that's what I'm looking for. So temperature final, temperature initial. Okay? They asked us to find what the final temperature was, correct? What will the final temperature be? Yeah? What did they give us? The initial. So what do you think I need to do to find the final? I need to first use my calorimeter equation and find change in T. Now you're like, well, Mr. Kramer, they didn't give us a specific heat. Well, we're using water. What is the specific heat of water? 4 point what? Okay, can we now plug in and solve for the change? And then once we have the change, find the final? Okay, let's do it. Okay, 942 divided by 50 and also divided by 4.18. I'm not going to do all that work, I'm just going to give you the answer here. The change in temperature is 4.51. When you do the math, since this is a relatively simple one to solve, am I okay not showing you all that? Then you're just dividing. Okay? Well, change in T is final minus initial. Can you plug these two numbers in and solve for your final temperature? You're looking at me like you're confused.
29.6.
Are you confused? Are you with me?
Yeah.
We know our change is 4.51. And we know our initial is 25.1. Add over, what was your final?
29.6.
29.61. Is that completely to sig figs, it should probably be 3, 3, 3, so it should probably be 3. Question?
I have a question on how we got the temperature, like is it
It's 4.5.
Oh, we got this number?
yeah, like, but if I multiply them together and then divide by 9.42, yeah, so.
Did you take this number divided by this, or this divided by that?
You do the
Oh,
change in temperature plus, look, look at the equation. Change in temperature equals TF minus
When you
TI.
plug it in, there's that negative there, and then you add it to the other side. Okay, any other questions on this? And this is actually one of the more difficult ones because we had to find something within the equation. Okay? That's one I think is going to be easier, and I'll let you do on your own. Okay? We're still in water. I'll let you do this one on your own. Can I erase this? What? Not yet. Still dealing with water, so that the reason why I said it, when you're still in water is why. What does that tell you?
That's specific.
Yep, that your specific heat capacity is that 4.18 number. Now, if in your homework they give you a different substance that's in the calorimeter, you're going to have to look up the specific heat capacity in your book. You have a list in your book. What? I'm telling you that. No, that's what you're putting into water. Wait. Hold up.
It's in the sentence.
Yep. So we have to find what silver's specific heat capacity is. Sorry. Well, do you guys have the chart in your notes?
No.
Okay. So there it is. Good catch there, Colby. I just kind of assumed it was silver put in water. So 0.23, everybody get that? Tanner, did you get all this in? Yeah. When you have an answer, raise your hand. I'll come around and check quickly to see how we're doing. Wasn't an overly difficult one. Yes, but I don't think the right one is sig figs. Put that in your calculator again. Yeah, put that in your calculator. Yep.
Yeah, but you only have.
Yep, so change in temperature is always going to be the final minus initial.
Wow, my mom loves that.
Okay, remember that change in is always final minus initial.
I want free ice cream.
Yep, put a unit on it though.
Oh.
My mom just said. A Dairy Queen.
Yep.
Yeah.
Okay, I didn't see every last one of you guys, but for the majority of you, I saw the right answer, so I'm assuming we're doing it all right. Did we get 450 joules?
Natalie wants to know why you didn't run that.
Oh. The specific heat.
Because I need two sig figs.
2.23.
Does that not answer your question?
To the place where the 5 is.
Because if you go 451, that has 3.
Yeah.
So I have to make that a
What are
0.
you saying?
But like
You're supposed to round up.
You're not rounding with the 8, you're rounding with the 0.
You're rounding here.
Okay, I get it, it's fine.
Was she trying to make you feel bad or something? Or what?
Yeah.
Oh, she
Well,
does
that's
not
what she always says.
Oh my.
That's kind of true.
Yes, we're for real.
Alright, here we go. This is an equation that's going to be used quite a bit. Okay? It's our first enthalpy equation. Remember what enthalpy really means?
Changing
You can do HPROD to abbreviate and REACTE to abbreviate.
Can we just do P and R?
Fine, do P and R. Do you be you. This is the world we live in.
Oh my.
I was about to say, don't do that.
Okay. So what this is we're going to be talking about the enthalpy or the amount of heat given off by the reaction. Okay, and we talked about every reaction has bonds breaking and bonds forming. Breaking bonds, what? Requires energy. Forming bonds releases energy. Okay? So, we've also talked about this concept here, correct, the other day?
Yeah.
We said negative change in H means exo, because when we think of negative, we think of energy leaving, correct? Right? And positive change in H means endo, because when we think of endo, we think of bringing energy in. Okay? So here is an energy diagram of what this looks like. Okay? In a situation here, I gave you the reaction for this the other day. This is the producing water. And we said in most cases, things react to become more stable, which means they go from high energy to low energy. Well, if you start at a higher energy reactant and you go to lower energy products, energy gets what? Released. Hence why you see the negative here. Okay? You have high energy reactants and low energy products, so energy gets released. So another way of saying this would be, it took less energy to break the bonds, and a lot of energy was released in the formation of the new bonds. Because didn't we say every chemical reaction has both breaking bonds and forming bonds? Correct? Every reaction.
Yes.
You will break the reactant bonds. Those atoms will now rearrange and form new bonds. Every reaction has those three things. Did you guys have like space to put this? Yeah. Okay. So now, here is an example of a chemical reaction that is not favorable, in that it actually would be more stable before it reacts. Okay? So we're going to talk in a later chapter that the only way to get this to react is to increase or put in energy. Some things require energy for them to react. Okay? So in this situation, we actually had low energy reactants, and the only way to produce the products was to absorb more energy than was given off. So it took more energy to break these bonds, and very little energy was given off when they formed these bonds. Okay, notice the sign of the enthalpy. It's what? Positive, because you have an overall net gain of energy, and that's why you see the products have higher energy than the reactants. Is everybody able to conceptualize the graph here? Understand that an exothermic energy is released in the process, endothermic energy is absorbed, and what that looks like. And now couldn't we then figure out the energy associated with the reactants, the energy associated with the products, use our products minus reactants equation that we just gave you, and couldn't we figure out the enthalpy of the reaction? That's what we're going to do.
So it's not products aren't stable.
In this case, actually the products are less stable than the reactants.
Why is everything wrong?
Most things won't react. The only way for this to even react is you'd have to put in a bunch of energy. Is this going to happen naturally? No. This will not happen naturally. It needs help.
So like, how do you know when something is real and when it isn't?
This is real. You can produce this.
No, but like, how do you, if you're like, you can tell that it's endothermic because it's like the products are going to be more stable. So how do you know if it isn't going to be more unstable?
Well, you'd have to know some inside information.
So if
I mean,
endothermic.
you would. Like you wouldn't be able to just look at something and go, oh, that's exothermic. Although if you see a reaction and a lot of energy is given off, that's a pretty good indication that it's exothermic,
There's a
right?
question on the test, it's just like, is this reaction exo or endothermic?
No, well, I could give you, if I gave you a negative change in H, you'd be able to tell that information.
Oh, yeah.
So
What does a negative
it's
change in H
all-
tell you?
It's
It's
exo.
exothermic.
Are all endothermic reactions the product of higher energy?
Okay, so I'm just going to show you this because sometimes you will see equations where heat is in the equation. Just want you to make note of this. You're probably going to want to write this somewhere. When you see the heat energy as a product, okay, it is exothermic. It is being released. When you see heat as a reactant, it is endothermic because it is required to react. Okay, so write that in somewhere. When you see heat as a product in a chemical equation, it is exothermic, heat is released. And when you have heat or your kilojoule number on the reactant side, it is required and absorbed and it's endothermic. Reactant is endo, product is exo if you see the heat in the equation. What you doing, Tanner? What?
Oh, it's got.
Making sure. Cool? Alright, this is really important for us to get a good grasp on. We're almost done here.
Is there a space button on a calculator?
You have a question?
There is.
Where?
It's on zero.
That's very bottom.
Okay, alright.
Zero.
Listen to me very carefully here. Molar enthalpy of formation. Let the word formation tell you what's going on here. Okay? What this is telling us is how much energy would it require to form something. Okay? Now, they had to set a standard somewhere. So what they said was, is if they are in their most natural state that you're going to see naturally in nature, their enthalpy of formation is 0. They're naturally that way. So any element that you see, like if you see just a lithium atom in an equation, its enthalpy of formation is 0. That's what it naturally is in. If you see something that's like hydrogen gas, H2, anytime you see a lone element by itself, the enthalpy of formation is 0 because it's naturally that way. Does that make sense? You're going to need to remember that. I want you to quickly, I want to show you this in your books. There's a big table somewhere in here. Where are you? Turn to page 344, 345. I'm going to be looking at this table quite a bit in the next few days.
Are we able to use it on the test?
I'll give you the information you need from this on the test.
That's chonkers.
Okay? Now, do you see the column that has change in H of F? That's the first column. Do you see it? That's the enthalpy formation of all these guys. The amount of energy either released or absorbed to form. Look at the very first one. What is it? 0. And the reason why is it's a lone atom that's in its natural state. The next few guys have an enthalpy value because those are chemically bonded. Now notice what the sign of the next 5 are. Negative. Why do you think they'd be negative? Most of the time, things bond to become stable, which means low energy, so energy is released. There's very few guys up here that have a positive formation value.
Wait, so how do bonds even form if they're becoming less stable?
You have to add energy to do it. They're not going to happen naturally.
So exo reactions are way more common.
Yes, naturally. Now, so what we do with like a gasoline, a lot of times we want to produce like gasoline, we have to put in a bunch of energy so that we can burn it to get more energy, get energy out. Okay, so yeah. Anyway. So I want you to make note that when it's in its lone state, so we're talking about any element by itself or any diatomic element by itself, what's the formation number?
0.
0. Okay? Everything else, you need to look at the chart, and we will spend a different day going over this more. Okay? But what you would essentially do, and we're going to do this on a different day, so you will take the values from here and you will plug them into that equation. We'll do this on a different day.
So since we didn't finish, do we still have the homework?
Yes, you got it.
So I remember what is the last your question?
That's like 100 points of that.
What?
100 points.
Can we talk more about that on
Because it's impossible.
It's
Unless you have the photographic.
bet.
Not like.
Depends on how we're gathering some of
I'm gonna
this
memorize that
information.
thing.
So,
They use
homes,
big words to make it make
we
sense.
might do a lab.
That's how my like brain works. Like I'll edit my sentence enough that it doesn't make sense to me.
Yeah, I get that. I have written so many things this
This class? In this chapter?
Yeah.
Wow. Only on day 2.
Yeah.
I heard it was a root day.
You heard wrong.
Dude, I'm so tired. It's gonna work one of these days. I'm actually so dead. I was like so almost out in history. Would you nap?
What? Can't do that.
I literally am not.
No, I'm using the word correctly because you literally never actually.
I'm not. Well, I'm diligent, Steve.
I'm surprised you didn't Bruce.
Look over there. That's why I'm sad. Find a solution.
This isn't any. Just.
I was like,
No, I had a decent idea.
I voted for you.
Oh wait, is this still on?
Hi, Mom.
No, most of the time,
Can you stop this
kids
thing?
act with their parents. You notice that your parents are not have a problem with authority, but like struggle with like being on time. Yeah.
No, but
No, I don't mean that in a bad way, because like I told you how much my son
you tie.
does the exact same things as me.
You like slant this over this way, and then get this out of here. So that way, it comes down the ramp.
Just like you.
That thing hits a ball. The ball comes down the ramp. That ball hits another ball. Or another thing that has a rope tied to it, which pulls this down.
We're using the trapdoor, by the way.
Oh, we are? Yeah. So we have to incorporate that? Okay, never mind.
Hey, that's on.
Yeah, I know. We noticed. I didn't want to shut it off.